Welcome, everyone. Today, we are going to get a handle on a huge concept in precalculus, how to move graphs around a page. And I promise you, by the end of this, it's going to feel like second nature. So let's just dive right in with this. I know, it sounds like a weird riddle, right? But the answer is actually super simple, and it connects directly to everything we're about to cover. It's all about one thing. That's it. It's just about moving stuff. The math behind this is the exact same math that a programmer uses to animate a character. And yeah, it's also the same logic you're going to need to crush those complex derivatives later on in calculus. Okay, so let's start with the most intuitive, the most straightforward kind of transformation there is, vertical shifts. These they just make sense. The key thing to notice here is that word outside. Think of it like this. The function, f of x, does all its work. It calculates the height. And then only after all that is done, we come along and just tack on a number. It's an afterthought. So let's take a look at a classic parent function, right? The basic parabola, f of x equals x squared. You can see its main point, the vertex, is sitting right there at the origin, at 0, 0. So what do you think is going to happen when we introduce that outside change? Since that +4 is happening outside the main action of the function, it's outside the part being squared, what does your gut tell you? Is that going to change its height, or is it going to change its position sideways? And yep, this shows the rule perfectly. Plus means up, and if it were minus, it would mean down. It's exactly what you'd expect. The entire parabola just gets picked up and moved straight up the y-axis by 4 spots. Easy enough, right? All right, we've got the easy one down. Now we got to tackle the tricky one. This is the one that trips up almost everybody when they first see it. We're talking about horizontal shifts. This right here. This is the single most important thing you need to remember. Just burn this idea into your brain. Whatever is happening inside the parentheses with the x, it does the exact opposite of what you think it should do. Now take a really close look at that formula. Y equals f of x minus h. That minus sign is everything. It's the whole reason this feels so backward, but it's also the key to getting it right every single time. So let's break down what it really means. For this one, our parent function is the absolute value of x, that simple V-shaped graph. And this time the change is happening on the inside. We've got a -3 right there next to the x, inside the absolute value bars. Okay, here it is. This is the trap. You see -3, you think negative direction, you think move left. But remember our golden rule. Input changes are counterintuitive. So if your brain is screaming, go left, what's the actual correct move? And there it is. A minus sign inside the function actually shifts the graph to the right, into the positive direction. But why? I mean, memorizing a rule is one thing, but if you understand why it works, you'll never forget it. So it is time for that aha moment. Let's finally pull back the curtain on why this rule works the way it does. Once you see this, it's all going to click into place for good. This is it. This is the whole secret. The function's home base, its starting point, is where the input is 0. So the function is always asking, hey, what does x need to be to get my input back to 0? If it sees x minus 5, well, x has to be positive 5 to cancel it out. If it sees x plus 2, x has to be negative 2. The shift is just whatever x has to do to compensate. That's the whole trick. So now that we actually get the why behind both rules, let's put them together and see how they work in the same problem. This is pretty much your cheat sheet. On the left side, you've got your outside changes, the vertical shifts. They're intuitive. Plus is up, minus is down. Simple. On the right, you've got the inside changes, the horizontal ones. They're counterintuitive. Plus means left, minus means right. Okay, let's try a more challenging one. Here we've got a square root function, and you can see it's being pulled in 2 different directions, both horizontally and vertically. So where do we start? You just take it one piece at a time. It's that simple. First, you look inside the function. We see x plus 2. Okay, inside is opposite, so the opposite of plus is a shift to the left by 2. Then you look outside. We see a -5. Outside is intuitive, so minus just means down 5. And the end result, the original starting point of that square root graph, which was sitting at the origin, 0, 0, has now picked up and moved to its new home, -2, -5. So why does any of this stuff really matter? Let's bring it all the way back to that first question I asked about video games. This is where it all connects. When a video game developer is writing code to make a character move, they are literally using this exact math. When they add a positive velocity to the x-coordinate, that's your f of x minus h. When they add a velocity to the y-coordinate, that's your f of x plus k. It's the same thing. You see, you're not just learning some abstract math concept here. You're actually learning the fundamental logic of movement in all computer graphics. Literally every time you see an object move on a screen, you are watching a function transformation in real time. So we've seen how adding and subtracting can move a graph all over the place, which leads to one final question to chew on. What happens when we bring multiplication and division into the mix? What do you think that does to the shape of the graph? Well, we'll dive into those stretches and shrinks next time.